Hello, welcome, welcome. So, in the previous episodes, we have been building up this processor from scratch, and it is now Turing complete in that it has conditional branches and it's able to read and write from memory. So, currently, there's a program in here that is executing the Fibonacci sequence, and it's filling memory with the numbers that it determines. So this is a very important and very exciting milestone. And to celebrate, I would kind of like to make this thing work in actual hardware, like on a FPGA. But there's a few issues with this processor as it currently stands. One of those issues is that it takes a single cycle to do all of its work. So it needs to fetch a instruction from program memory, and that takes some amount of time. And then it needs to decode that instruction, which should be fairly fast. It's just a few multiplexers and some AND gates. Then it needs to figure out what the instruction is going to do, which is another layer of AND gates. And then it needs to execute the instruction, which for an add, you have to wait until the carry propagates all the way to the very last bit. So that can take some amount of time. It's fairly slow. And then in some cases, you have to wait for that carry bit to go into the control logic to be registered. But then in other cases, you have memory access, and memory access can be quite slow as well. So you'd have to add two numbers together in order to calculate the address. And then you have to send that address to the memory, and the memory will take some time to calculate where it is that it'll find that value, and then you need to read it out. And we already encountered an issue where we tried to use block RAM, but block RAM will only provide the value on the very next cycle, right? So we had to use this RAM, which I'm not even sure how that's implemented in an FPGA, because as far as I know, most of the memory in an FPGA is block RAM. So I don't even know if this would even run on an FPGA. And then, of course, we've got to write everything back to the register file, and that'll take some time as well. So this is a very simple processor, and it looks very nice, but it can't actually run anywhere but in simulation, which is, in my books, a bit of a problem. So I've been doing a little bit of thinking about how we could do this, and it boils down to this processor needs to take multiple cycles to execute an instruction. That's really it. I mean, it can't continue to execute everything in a single cycle. Now, what I would like to do is split it into probably two cycles, I think. A fetch cycle and an execute cycle. And occasionally, if it's doing a memory operation, then it may need an extra cycle to do that. So given that, there's a few different ways that we could do that. We could set up a sequencer within the control logic, which, by the way, I have cleaned up a little bit. I added some labels and I added some test cases to the control logic. So we could, in here, set up a sequencer, and it goes through a series of steps. And the first step, of course, would be the fetch. And then the next step would be execute. And occasionally, it would need maybe another step or two. So that's one way to do it. I actually don't like that idea. And I came up with a different idea. And one of the reasons I don't like that is it ends up that now you've got a sequence value that you have to put into all of these AND gates. So they get another input. And there's pros and cons to that, but there is another way. And it involves just adding perhaps just one input into this. And in fact, it might even be simpler than that. So I'd like to try that in this episode. I'd like to see if we can halt the processor. So what I would like is an input, I guess. Did I say halt? I meant stall. I'd like to be able to stall the processor. So let's see if we can do that. So we'd have a stall line. I wonder if there's a different way to do this. I'm going to go with this for now, and I'm going to make it default to high. So when we turn on the power, the stall line will be high, and so it'll start in the stalled state, and we can release it from stall by clicking here. That way the clock can be set to on all the time, and we can just start it running by clicking on the stall. So what do we need in order to stall the processor? Well, if you think about it, there's at least two different things that we need to stall. One is any kind of writes that happen on the right-hand side of the processor here. So we want to make sure that we don't write to the register file, and we want to make sure that we don't write to the data memory. So this store line would have to be held low. So that's one aspect. There is actually another register hidden in here, and it's in the control unit. And maybe it shouldn't be in the control unit, but there's a T-bit register right here. So there's actually an enable line on this register that we can hold low to make sure that the T-bit isn't written. So the goal here during a stall is not to write anything, not to change any state. We don't care if we recompute the state. We just don't want to change the state, right? So we can compute what the next state will be. That's fine. And if the answer changes in the next cycle, that's fine. We just don't want to change anything. We don't want to commit, in other words. So we need to run the stall line to all of those. But there's also another aspect on the left-hand side here. We don't want to increment the program counter, right? So the program counter has an enable line here that will cause it to increment, and we don't want to do that. But the reason I want to keep these two signals separate is, for example, if memory access takes 2 cycles, it can hold a line high that says, hey, don't fetch, right? So fetching is one of the key things that will move the processor forward, right? And that involves incrementing the program counter and fetching the next value. Well, if we just refetch the same value, then that should be fine, right? So we could have something in the memory access that asserts a control signal that says, don't fetch, don't increment the program counter. And potentially that line would also actually inhibit everything else except for the store on memory. So I think it makes sense to have a few different signals that this goes into, and we can have OR gates that control which of those signals are active in which circumstances. So without further explanation, let's see if we can get this implemented and working. So for now, the stall line is just going to disable all of these. So I guess it needs to be inverted, which is easy enough to do. So if the stall line is low, then fetch will be enabled, memory will be enabled, and the register write will be enabled. But if the stall line is high, then it'll disable all of these, if that makes sense. And then we can selectively enable these as needed. And one of the things that we want to do is when the registers are enabled, we want to enable the T-bit to be set. So we might as well do that while we're here. All right. So I think this should work. We have to have the memory enable active in order to store to memory. We don't care about loads necessarily, although in the future we might, but we definitely want to ensure that the store line can't go high if we're not enabled. So this should work. I wonder though if we actually do need an extra enable signal. I mean, in keeping things simple, the less control lines, the better. And this is an extra control line. We have a mem signal here that will suppress a store if it's low. So I think maybe we should use that instead. Now, it'll cause different things to happen up here if that signal is low, which is why I was thinking we should add it. But yeah, I'm thinking maybe we shouldn't. Yeah, instead, let's try and get that line to be low. So in that same spirit, actually, we could inhibit the ALU so that it'll emit a NOP and won't do anything if it's not enabled. So I think that's probably the best plan there. So let's do that. So if the stall line is high, then memory is not enabled, so the memory line goes low, as we can see down here. And then the enable register line goes low, putting a NOP into the ALU, which, by the way, we don't have to implement it as a NOP, but it's less control lines out of here. So less control lines out of here is better because it keeps the rest of the processor simpler, and we're taking advantage of a signal that we're already sending out. So I think that's a good idea. So in here, we want to implement the enable line where it will enable incrementing the program counter in the next clock cycle, as well as if it's not enabled, it shouldn't write the program counter. So we should inhibit the load. So let's do that. It might actually already inhibit the load. Let's look through the help here. Doesn't actually say. I suppose we could figure it out with, yeah, let's see if we can figure it out. Yep, it does indeed write, and we want to inhibit that if it's not enabled. So we need a bit of logic in here. Okay, I think that should work. Yep. All right. So we have an enable signal. We have an enable signal here. Let's rearrange some pins here. Hmm. Okay, so this is the one that I wanted to make sure would work. So we've got a mem line that enables the store, and if it's stalled, all of that goes dark, which is good. So we have the ability to stall. So we could actually redo the clock circuit here to use the stall. Yeah, we could redo the clock circuit to use the stall, and then we can advance, or we can run the processor. So that might be interesting. Let's do that. Let's create a new embedded circuit called clock control. So what I want to do is have the step input create a pulse for only a single clock cycle. And that's a little bit tricky to do. I've tried to do this before and had a lot of difficulty with it. I think what we want to do is I don't think so. Because we could do this and then I guess do this. And this will work, but there's a bit of a race condition in that, well, potentially I can demonstrate. Let's just give us a output here. It might be okay. What I'd want to know is this creating a pulse when that happens? I guess what I would need is a way to reset it. So we have a clock line high and the step line high. It doesn't look like it's creating a pulse. That's good. If the clock line is low, then it goes through. Okay, this looks like it's going to work. So what this D flip-flop is doing is it's making sure that the clock line is high for an entire clock cycle. I'm not 100% sure it's required, but yes, it is. It is required because the step, you could push the step button at the very, very end of the clock cycle, and then it ends up having a super short clock cycle. So that's not so important in the simulator because the simulator doesn't simulate proper propagation delays. But in real hardware, it's quite important that that happens, including on an FPGA, because the FPGA timing is based on having an entire clock cycle to do the work. So that's why this is set up that way. So we also have a run, and I would like to be able to just push this button and it'll run the clock until the step button is hit again. So let's see if we can implement that. There is a bit of a bug in that if the clock line is high and you step, then it'll ignore the step, which is not really what I want. I'm not sure what to do about it, though. Maybe I'll solve that bug some other time. It'll probably take me a little while to figure it out because this sort of logic really hurts my brain. But this works well enough. Well, yeah, it starts stalled, which is what we want. And the clock line won't do anything until either we hit run and then it'll just run, or we hit step and it'll do a single step. Okay. All right. I think this is good. And the nice thing about this circuit is we can put these buttons out to actual push buttons on an FPGA, and we can single step the processor and see what it does. And we can hit the other button to just run it, which will be very handy. So the problem with the step button going high during the clock pulse and it ignoring it seems to happen a lot more frequently than I thought. But at least the run button works, and we can step to stop it, and we can single step or potentially single step. Takes a few tries, which is a little annoying. Holding it down doesn't seem to help. Yeah. Okay. I think this might work better. We have the ability to send a single clock pulse. Now, the step button has to be high while the clock goes high in order for it to be registered. So that might be a little bit annoying if the clock is really slow, but we get a single pulse, and we've got run where it'll run the processor until the step button is pressed, and then it'll stop it. So I think this will work. Let's try it out. Okay, we start in a stalled state. That seems to be fairly reliably running. Awesome. And then we can run and stop. Awesome. Sweet. Awesome. Okay. Well, I think that is everything that I wanted to do in this episode. We now have the ability to stall the processor if it's running on a very high clock speed device. And we've got a line that does that without having to have any of our clocks stop. And it's important not to stop the clock or to gate the clock, because that can cause race conditions and can also cause inefficiencies in how the processor gets wired up inside the FPGA. So we want the clock to continue running. We just don't want the processor to actually do anything unless the stall line goes low. And then if the stall line goes low, then we want to actually run. So this is an important step in the right direction. There's a few other things that we need to fix. One being we need to have fetch happen in a separate cycle from the rest of the processor, but we can do that in a future episode. So if you have any questions, feel free to leave a comment down below. Thank you very much for watching, and I hope you have a great day. Bye.